Hi, my name is Casey Chu, and this is joint work with Kentaro Minami and Kenji Fukumizu. Our work deals with the central question, why do some GAN variants seem to be more stable than others? Our work provides a new theoretical framework to answer this question. As a quick review, GANs can be thought of as this minimax problem, where we have this loss function J that takes in a generator and a discriminator. We maximize with respect to the discriminator, and then we minimize with respect to the generator. The hope is that by solving this saddle point problem, the generator ends up matching the data generating distribution. Depending on the exact form of J, we end up getting differing behavior, aka different GAN variants. So our analysis goes like this. We say, what if we box this inner maximization problem, and call it a function f of theta? Now, f is a function of just the generator parameters, and only the minimization problem remains. So now we can view the GAN training process as simply gradient descent on this function f of theta. Therefore, we can analyze the behavior of gradient descent using some classic optimization theory. In particular, we rely on this fact that gradient descent is stable if f is smooth in the sense defined here. This leads us to a natural question. Which GAN variants out there give us a function f that actually satisfy this smoothness property? Well, the smoothness of this f is actually quite difficult to analyze directly. That's why we derived this theorem that decomposes the smoothness of this function f into two parts, conditions on the optimal discriminator of the GAN and conditions on the generator architecture that we use to parameterize the generator. So to check whether a particular GAN variant is stable in the sense that we described, all we need to do is check whether the optimal discriminator satisfies these smoothness conditions, D1, D2, and D3. Unfortunately, many existing GAN variants actually don't satisfy all these conditions simultaneously. But there is a glimmer of hope, since these three GAN variants at the bottom actually do satisfy some of the conditions individually. Now here's the cool part. We're going to combine these three GANs here into one super GAN that simultaneously satisfies D1, D2, and D3. To do so, note that these three variants minimize the Wasserstein distance and integral probability metric and the maximum mean discrepancy. To form our super GAN, we're going to construct a distance function that the GAN will minimize that merges the Wasserstein distance, the IPM, and the MMD. And in doing so, it inherits the smoothness properties of these three GANs. And it turns out that the resulting GAN satisfies D1, D2, and D3 simultaneously. The secret weapon that we're using to do this is something from convex analysis called the inf convolution. And the intuition is that the inf convolution combines loss functions in a way that preserves the minimizers, but also retains the smoothness of both functions. Now, how do we implement this GAN in practice? Well, we use convex conjugation to interpret these inf convolutions as regularizers on the discriminator. And it turns out that these discriminators actually match a lot of what is used in practice. For example, spectral normalization and gradient penalties. We therefore recover a lot of existing GAN regularization techniques. So what have we done? We've developed a new theoretical framework to analyze the stability of GANs. We found that some GANs satisfy the smoothness conditions, but not all of them at the same time. And finally, we motivate several regularization techniques from first principles. Please check out our paper. Here's the link, and here's the QR code. And thank you so much for listening.